This is a test run of the OU Tulsa recording studio. I'm going to be presenting this. This is mutual information between regional EEG electrodes as a function of distance by me. Yeah, where should I be looking? Here. Where's the camera? Oh, there's the camera. Okay, cool. So, yeah, I'll first introduce you to the question. We'll talk about how the question came up, some of the context, and then I'll get you started on some of the background and the core concepts that you need to be aware of before we start talking about the experiment itself. And then we'll start talking about how I designed the experiment, and we'll get into the results and analysis, so what came of the experiment. And then, of course, we'll get into some references in case you want to read up a little bit more. So yeah, this presentation is pretty much very closely related to my thesis research. So first I'm going to introduce you to my thesis research, or at least the high level of it, and then we can get into what this presentation is about. So my research is really centered around this experiment where we bring a subject into a room, right, and they're sitting down and they hold this they're holding this grip tester thing. I don't know if you've ever used one, but first we tell them to relax their hands so they're not squeezing at all. And then we tell them after a certain period of time to squeeze it at about 80% of their power. And they hold this until we tell them to let go, and then they let go and relax again. And essentially we have them do this a ton of times, multiple trials, multiple patients, multiple days. We got a lot of data. But the whole time we're doing this, we're recording two things. One, we're recording the electrical signals in their brain. And two, we're recording the electrical signals in their forearm. As you can see on the left, there's a ton of places that we're measuring electrical activity on your head. It's actually 64 exactly. That's the one we used, a 64 channel EEG. And then we're also measuring the electrical activity in the muscle, right? And we're measuring it in 4 places. As you can see on the diagram there, I think that's 3, but you'll see on the next slide is 4 actually. And if you go look below the pictures of the instruments and see the data itself, that's volts versus time. So electrical activity, right, volts. And you can see starting on the right, you can see that in that region there's a clear difference between what's in the region of green and what's not in the region of green, right? And you could probably guess what that region of green means, right? We have low amplitude activity and then high amplitude activity and then low amplitude activity, and that corresponds to rest, squeeze, and rest, right? But on the left here you can see that, and by the way, this is one channel, not some kind of amalgamation of all 64 channels. It's one channel, and you can see it's not very clear what's happening, right? It's just a bunch of noise, a bunch of just ups and downs, and it's not immediately clear that there's some kind of marked difference during that green period of squeezing. You could argue that there's a bit of a reduction in amplitude, but as we collected more trials, we saw that that's not always the case. So I guess that's debatable. But either way, it's kind of unclear how exactly we can tell when someone's squeezing from their brain data. And so that's the goal of my research, is to be able to find, in particular, a transfer function that relates that EEG electrical data during the squeeze to EMG electrical data during the squeeze, so that we can kind of predict what's happening here from what's happening up here. And So to simplify my research problem, I decided to narrow down this investigation into relating a waveform at a specific point, specifically the left motor cortex, as you can see right here, where we at? Right here, electrode C3, that waveform, to the waveform at your flexor carpi radialis. That's the muscle that's heavily involved when you squeeze something. And so that's something I did to kind of simplify my experiment, right? But the question is, how much am I missing out on by only using that C3 electrode, right? I chose the C3 electrode, by the way, because one, the patient was squeezing their right hand, which means the electrical activity, the relevant electrical activity in the brain is probably going to be happening on the left side, right? That's how the brain activity works when you're moving. If you're moving one side, then the activity is going to be on the opposite side. So I chose the left side for that reason. But I also chose C3 instead of C5 or C1, which are the electrodes right next to it, because C3 is centrally located over the motor cortex. But I could have easily chosen C3, C5, and C1. So my question, again, the question of this whole presentation actually is, how much am I missing out on by excluding C5, C1, or even the other electrodes in the motor cortex, which could be on the right side, like C2, C4, or C6. This is where information theory comes in, right? It's tough to kind of quantify how much information I'm missing out on without some of these concepts, as I'll show here in a minute. This slide, I wanted to show you a bit about, see this yellow region. I'm still getting used to using this thing, this recording studio. Here, this yellow region is the motor cortex. So that's where this the relevant activity, the activity related to motion is going to happen, and that's these 7 electrodes right here. Like I mentioned, C5, C3, C1, C3, C2, C4, and C6. And so, essentially, one of the concepts that we have to consider, like I said, is that all these electrodes are all related to movement activity. So maybe they'll contain the same amount or same information. Maybe they won't. That's one thing that we could investigate, or we may find out as a result of this experiment. And then the other thing that we should consider before going into this is it's a very important concept in EEG, in the use of EEG and understanding EEG data. So essentially, we have these sources of electrical activity, right? And how the brain typically works is sections of the brain fire together, right? They synchronize at times, depending on what's happening in the brain. And these are the signals that we're picking up on, right? So you can see there's some, they call it local synchrony here, and then there's some local synchrony here, and they each emit a certain frequency, right? They synchronize to a certain frequency. And essentially, we want to pick up on those frequencies, or those oscillations, right? But there's a lot of things that happen to those oscillations before we can get to them, since we're recording from outside the brain. One thing is the interference between these the signals in different places, right? They might destructively or constructively interfere, so we might be getting a mix of these two. So this, let's say this electrode, we're looking at this electrode here, it might be picking up a mix of this electrode, where are we? This electrode, or this activity, and also this activity as well. Another thing that happens is it goes through so many layers. It goes through, the signals go through the dura mater, the pia mater, and then it goes through the skull and the skin and oil and hair, and then it goes to the electrodes. So what happens is the amplitude of the signals are drastically reduced, and the amplitude of noise in comparison to the signal is increased, right? Your SNR is crushed. Another issue is that, like I said, it goes through the skull, and what happens when it goes through the skull is that the signals come up here, right? Jeez, the signals come up here, and once they hit the skull, they spread out, right? So this signal comes up here, and then it spreads out in this direction, it spreads out in this direction, and so you're going to get a little bit of the signal in this electrode, and this electrode here, and this electrode here. So essentially, there's just a bit of a mess happening, and you can pick up on activity that's happening in certain areas, in the local areas, but you won't be getting a perfect measurement of what's happening at that exact point. You're really getting a measurement of what's happening in that area. And so that's kind of leads to my next point, that increases in spatial resolution in EEGs results in diminishing returns after a certain point, right? So if, let's say, you added more electrodes in between these electrodes here because you want to get a more accurate reading. The question is the signal that you pick up in between these electrodes, right, about there, right here, is that going to be much different from the electrode, the signal here, or the signal here? And how much different? How much different is it going to be? And that's essentially what this presentation is about, right? I want to quantify how much different the signal at this electrode is from the signal, at this electrode right here. I want to quantify that, and we can do that through mutual information. Mutual information is one of the core principles, one of the core tenets of information theory. So let's get into how exactly I did that. So first, I decided to focus this presentation on these 7 electrodes, right? I think we're on the left side here. So C5, C3, C1, CZ, C2, 4, and C6. These 7 electrodes, which go like right here, are the motor cortex electrodes. And so what I want to do is figure out how much different the information in all of these electrodes is, right? So the first thing I did was I got the time series voltage versus time plot for each of these, right? So we had this EEG on their head, it was running, it was collecting voltage versus time data, right? How that voltage changes over time. And this is what it looks like. You see this number here is about, where are we at? I don't know why I keep looking here like I'm going to see something. There's nothing here. For me, there's nothing here, but for you guys, there's something. So there's about, let's see, 500,000 samples. And sampling rate is about 1,000 hertz, so we're looking at about, the sampling rate is 5,000 hertz, so we're looking at about 100 seconds of data. And so what I did was I took this time series plot and I turned it into a histogram, right? And so essentially, to get from a time series plot to a histogram, all you really do is you take this graph, you shift it, and you just let everything kind of fall. You know, you're shifting the axis in a way. And so these are the histograms you get from that data. And you can see there's different distributions for each of them, right? Different things happening. And if we've studied mutual information, you know that once you have a distribution, you can find the entropy of that variable, because we're treating all of these electrodes as random variables. And so this is essentially, once we have the entropy, then you can find the mutual information between 2 electrodes pretty easily. And so this first part up here I'm going to stand up. Stand on this side. So this first part here is really tells us how we can go from entropy to mutual information, right? So we have Hx, which we calculate using this equation here. It's really just a function of the standard deviation or the variance of your data, right? So the variance of this distribution is going to directly just determine your entropy of that random variable. And then for the joint distribution of these two random variables that we're comparing, we're going to use, there we go, we're going to use this expression, this formula, and this is really a function of the covariance between these two random variables. And so once we find those values for each of the electrodes that we're comparing, we really just plug and chug, and we result in a mutual information between those two electrodes. And so I did this process for let's say we start at C5. We found the mutual information between C5 and C3. And then I found it between C5 and C1, and C5 and CZ. And I did the same thing for all of them, right? So the mutual information between all of these. And then we can do it also for C3. We can compare the mutual information for C3 and C1, C3 and C3 and C5, C3 and C1, and so on. And you do that for each of these electrodes. And you'll end up with a table that looks something like this, right? This is going to be the defining graphic of this presentation. So essentially how you can read this is, first, just recognize that this list of electrodes here, C5, C3, C1, is the increase. It's basically x. It's like a distance axis, right? So as we go in this direction, the electrodes become farther from each other, right? So C3 is far from C1 is farther from C5 than C3 is, right? And then C6 is the farthest electrode away from C5, right? So this is distance, increasing in distance. And essentially, right, so this first box here is the mutual information between C3 and C5. And let's say here, this last box is the mutual information between C6 and C5, right? And that's how you read this, basically. You can find two electrodes, find the mutual information between them. All right, so what do we expect the results to look like? Well, the first thing that we can expect, right, is if we're thinking about that concept we discussed before, right, electrodes that are closer to each other are probably going to pick up on the same types of signals, right? And so what we can expect is, right, electrodes that are closer to each other can also have similar or more mutual information, right, because they have some of the same information. So you can expect that these electrodes that are closer to the diagonal are going to have higher values than electrodes that are farther away from the diagonal. That's what we're expecting, right? And maybe we might even see something like high values here, and then lower, and then lower, and then lower, and then lower, and then the lowest values out here. Maybe that's something we can see. That's what we expect anyways. Okay, just a technical note. We have 5 data sets, and we can calculate a table for each of these data sets, right? And then we can average them to get this magical final data set. That's what I did. So let's get into the results. What is this going to look like? Are we right? Are we right in our assumption? So a lot of numbers here. You could go crazy looking at this table. We're going to look at a few key points and compare them to our expectations, right? So the first thing we can look at is let's look at this top row here, right? So remember, this top row is basically a way of expressing what the mutual information is of C5 compared to these electrodes as they go away from C5, right? So we expect the mutual information between C5 and C3 to be high, and then the lowest mutual information to be the farthest away from C5. So let's look at this. We have 0.203, cool, and then we have about 0.06, so that's lower. So the mutual information between C1 and C5 is lower than the mutual information between C3 and C5. And that makes sense, right? Because C1 is farther away from C5. Okay. Let's keep going. So we have C1 is 0.06, CZ is 0.005. So that's even lower than the mutual information between C1 and C5. Okay, so we're right so far. And then C2, the mutual information between C2 and C5 is 0.0567. That seems higher than the mutual information between CZ and C5. That's interesting. So basically what that's saying is the mutual information between C2 and C5 is higher than the mutual information between CZ and C5. That's not what we were expecting, right? We were expecting just lower and lower mutual information. Interesting. Let's keep going. C4, we see an increase actually in mutual information from C2. It's 0.12. It's pretty high. Not quite as high as our our adjacent electrodes, but still pretty high. And then finally we have about 0.09. It's a decrease, but still higher than some of the electrodes that were considered closer to C5. So we're wrong in our assumption that there's just going to be a decreasing mutual information as distance increases. So in that assumption, we're not exactly right. But let's check one other thing. We also assumed that we were going to have our highest values to be on the diagonal, right? Let's check that, right? So point 2 was the highest value in this row. So let's see here. 0.2 again, 0.205 compared to all these values in the row. And it looks like it is still the highest value. Okay, let's keep going down the list. So we have 0.44 highest value, 0.15 highest value, 0.1376 is the highest value, and 0.1962. So what does this mean? This means that for each of these electrodes, the electrode that has the most mutual information with it is the one that's right next to it. That seems like common sense, right? But at least we were right in that assumption. Okay. One other thing that I want to point out before we wrap this up was there's an interesting thing that you can investigate, right? So the question is, this new question is, let's take C2 for example, electrode C2. Which of the adjacent electrodes shares more information with C2? Right? Does C4 have more information, share more information with C2, or does CZ share more information with C2? It's interesting, right? And we will get two different numbers for that. So let's see which one it is. I'm gonna look here because so we said CV and C2 versus C4 and C2, right? So let's find this. C4 and C2 is about 0.1376, right? And then C2 and CZ, we're looking at about 0.15. So it looks like C2 and CZ actually share more information with each other than C4 and C2. What does that mean? Well, it could mean a number of things actually, but one interpretation could be that maybe there's more centralized information happening, more of the most of the more powerful or relevant information is coming in between. I really wish I could get this right, but I mean physically, yeah. But anyways, there's more information happening in between C2 and CZ in that space in between them than in between C2 and C4. That's one interpretation of it. There's a lot of different ways you can go with it. You could but that was my interpretation, is that that's where some of the localized information is happening. And then let's do this one more time. Let's say CZ and C1 versus where are we at? C1. So okay, so C1 share more information with CZ or C3. Let's see which one it is. C1 and C3 is about 0.205, and C1 and CZ is about 0.44. So there's actually a lot more information happening between C1 and CZ than there is between C1 and C3. So maybe I'm gonna get this right. I have to. So maybe there's more information happening here in between these two than there is here. Either way, this is an interesting table. Hopefully going forward we can get a more surefire representation of these relationships. This is averaged over 5 data sets, and I can guarantee you that's definitely not representative of a verifiable, something that's the law, very accurate. You'd have to average a lot more times to get this to be something that you can look at as information or as a reference, right? So that's one thing. Maybe in the future we can do more rounds of this. Other things that we could do is check out different brain regions, right? We only looked at the sensory motor cortex, or actually just the motor cortex. What if we did the whole brain and found an overall map of the relationship between everything, right? Wouldn't that be pretty cool? But that also brings into question, what about task-based relationships, right? So in this experiment paradigm, there was something specific happening, right? Somebody was holding something, focusing on squeezing, focusing on not squeezing. And so what would that relationship, the same relationship that we investigated in this presentation, what would that relationship look like if that person was sleeping, right? It probably, I don't know for sure, but it probably would look a little bit different, right? So it would be interesting to investigate what that relationship looks like when somebody's doing something totally else, right? And if we're going back to that possibility of investigating the relationship between all of the points in the brain, or at least in the EEG, then that definitely will depend on the task at hand, right? What the subject is doing. And then that last point, investigating maybe what that mutual information relationship looks like when you have more electrodes or when you have less electrodes. And we can go into that investigation kind of expecting that we'll have more mutual information in adjacent electrodes, right? If there's more electrodes. Meaning, let's go back to a slide that I think will illustrate this perfectly. This slide right here. So let's say this is where the electrodes are placed in the 64 channel EEG setup, right? Which is the one we used. What if we double it and we make it 128 channels? That means there's going to be an extra electrode in between each of these electrodes. So what are we expecting? We're expecting a lot more mutual information, right? Because they're so close to each other that they're definitely picking up similar signals. If we can expect in the 64 channel EEG electrode that they're picking up similar signals in adjacent electrodes, then if there's even more electrodes, we'll definitely expect the same thing at a much higher magnitude, right? And if we reduce that, then we might find that if we reduce the number of electrodes to 32 channels, then we might find that this effect that we're seeing is lessened, right? The mutual information between electrodes will be lessened, reduced, because they're farther away. That's what we're expecting anyways, if we go into something like that investigation. Yeah, so these are my references. They really have to do with some of the literature on localization, some basic concepts about central nervous system and brain function. And feel free to screenshot, use them as you will.